Hello students, today we are discussing the unit number 5, that is the frequency domain modeling and analysis. So these are the contents of the unit number 5. So in that first we discuss the transfer function based modeling of mechanical system. So there are two types of mechanical based systems. First one is the translation mechanical system, second one is the rotational mechanical system. So first we did in detail discuss the mechanical translation system. So in the mathematical modeling of mechanical translational system, so what is the translation system? Translation system, the system which moves along a straight line. So it moves in the straight line path. So main basic three components of these systems are, first one is the mass, then spring, and next one is the damper or a dashpot. So in depth, the each component we discuss, that the first component is the spring. So K is the stiffness of the spring, X is the displacement of the spring, and F is the force applied on the spring. So we know the deflection, spring deflection, distance x in proportional to the force. So spring stiffness is the force per unit displacement, so or a deflection. So spring stiffness or force generated due to generated in the spring, Fk is equal to k into x. If in the first case the spring is connected to ground and another is connected to the applied force, so in second case the both ends of the springs are open, so there are two displacement x1 and x2. So when we take the one end, then Fk, we get the k, that is the stiffness, into displacement 1 x1 minus x2. For n2 it is, we considered first, that is the x2 and then x1. Okay, then second one is the damper or dashpot. So best example of this damper or dashpot we can use in the suspension system. So x is the displacement, c is the damping coefficient, it is also denoted by the letter b, v is the velocity. So the force required to move the piston is directly proportional to the velocity. So damping coefficient c is equal to force upon velocity. So Fc is the damping force and it is equal to damping coefficient into velocity. So velocity is nothing but rate of change of displacement with respect to time. So we can take it as a c dx upon dt or b dx upon dt. In the first case, one end is ground and another end having the force, or it is connected to another element. If in the second case both ends are open, so for the one end, so equation is Fc is equal to c, so velocity at one end dx1 upon dt, and velocity at another end, that is minus dx2 by dt. So we can replace the c with b. Notification, there is a change in the notification only. Similarly for end 2, Fc is equal to c. So for the end 2, velocity at displacement 2, we considered dx2 by dt minus dx1 by dt, and is equal to b, notification change in the notification, so dx2 by dt minus dx1 by dt. So next important component, that is the mass. So force required to move the mass is the mass into acceleration, that is the force is equal to mass into acceleration. So acceleration is nothing but the rate of change of displacement velocity with respect to time. So velocity is nothing but the rate of change of displacement with respect to time. So we can change that equation to m d square x upon dt square. So m is the mass, a is the acceleration. Okay, so these the linear system, so these are the translation systems. So we consider one numerical. So this is the numerical of the first that is the mechanical translation system. So statement is the write the differential equation governing the mechanical system shown in figure and determine the transfer function. So we know the transfer function is nothing but Laplace transform of output to the Laplace transform of input. So this system is given. So having the two masses, one mass having one spring which is connected to the mass 1 and one is ground, another mass m1 is connected with the damper which is also ground and connected to the mass m1, having the displacement x1, mass m2 having the displacement x2, and having and applied the force on the mass m2. In between mass m1 and m2 the spring x2 is connected. Spring x2 is connected. So how to solve this numerical? So wheel shows there is a no friction, it is a frictionless, so we cannot consider the frictional support. Okay, so for we can apply using the step 1. So in the step 1 we use the free body diagram. So for mass m1 we take the free body diagram. So displacement is in x1 direction, so the forces, the spring force, damping force, and mass force, that is the inertia force, so these forces applied in the opposite direction for the balancing. So we taking the fk1 for the force induced in the spring fk1, fc1 force induced in the damper c1, fm1 inertia force, and fk2, this fk2 is nothing but the force through this spring k2, fk2. Similarly for mass m2 we take the free body diagram. So in the for the mass m2 displacement x2 in this direction and applied force f is in this direction. So here only the spring is connected and f force is applied, so f applied we shown here, fk2 opposite to the displacement, and fm2 that is the inertia force opposite to the displacement. Now the second step, that is the important one, the details of the components. So we for the mass 1 m1 and for mass m2 we take the details of these components. So m1, that is the force applied in the mass m1, is equal to m1 into acceleration. So displacement is x1, so d square x1 upon dt square. So another is the damper connected to the ground and mass m1, so fc1, so c1 is the coefficient into velocity, so velocity is rate of change of displacement upon time, so dx1 upon dt. fk1, so spring is connected to ground and mass, so it is only k1 into x1. So special case is fk2 because it is connected to the mass m1 and m2. So for the when we consider the details of component for the mass m1, so fk2 is k2 into displacement of mass m1 minus displacement of mass m2, so k2 into x1 minus x2. For similarly for mass m2, fm2 is equal to काय आलं fm2 is equal to m2 d square x2 upon dt square, and fk2 is equal to, now this special case, k2 for the mass m2 it is x2 minus x1. Okay, now next one is the step 3 for mass m1 by Newton's second law. By Newton's second law, f m1 plus fc1 plus fk1 plus fk2 is equal to 0. Summation of forces, it is equal to 0. Now we can elaborate that equation by putting these values. fm1's value is m1 d square x1 upon dt square, fc1 value is c1 dx1 upon dt plus k1's value k1 x1, k2's value k2 x1 minus x2 is equal to 0. So this is the first differential equation for the mechanical system for the mass m1. So for every mass we get the one differential equation. So there are two masses, so we get the two differential equations. So for mass 2, by using the Newton's law, so in the mass 2 the force is applied, so F it is equal to Fm2 plus Fk2. F is equal to m2 d square x2 upon dt square plus k2 x2 minus x1. So it is the answer number second. So these are the two differential equations we can get from the follow given system. So next one we have to determine the transfer function. So transfer function we require the Laplace transform. So for equation 1 we taking the Laplace transform with initial zero initial conditions. So d by dt notation s and d square by dt square is equal to s square. So this one is the first equation. So m1 and here is the d square upon dt square. So it is nothing but s square x1 yes plus c1 here d by dt is there. So yes yes x1 yes plus k1 x1 yes plus k2 x1 s minus k2 x top s is equal to 0. So we collect all the x1 terms and transfer x2 terms on the other side of the equation. So m1 s square plus c1 s plus k1 plus k2 x1 of s is equal to x2 k2 x2 of s. So we generate the equation in terms of x1 of s is equal to k2 m1 s square plus c1 s plus k1 k2 k1 plus k2 into x2 of s. That is the equation number 3. So now we're taking the Laplace transform of equation number 2 with zero initial conditions. m2s square x top s plus k2 x top s minus k2 x1 of s is equal to f of s. So s square is nothing but d square upon dt square. Okay. So k2 x top s minus k1. So we again simplified this equation and taking x2 terms and x1 terms separately. So putting the value of x1 s from the equation 3. So m2 square plus k2 x top s minus k2, this equation this value is from this equation we can put here. So again we simplify that one. So m2 square a common term x2 of s we can take it outside. So m2 square plus k2 minus k2 square divided by m1 square plus c1s plus k1 plus k2 x2 of s is equal to f of s. So we can simplify this equation. So m2 square plus k2, so cross multiplication is there, m1 square plus c1 s plus k1 plus k2 minus k2 square divided by this term. So the transfer function of the system is transfer function tf is equal to x top s divided by f of s. Output Laplace transform of output to the Laplace transform of input. It is equal to, so it is m1 square plus c1s plus k1 plus k2 divided by m2 square plus k2 in bracket m1 square plus c1s plus k1 plus k2 minus k2 square. So this one is our final answer.